Hi everybody, this is Ms. Burko and I'm going to take you through the 2.1 notes that'll help you get ready for the 2.1 Ready, Set, Go. So the first thing we're going to do to get ready is talk about some of the vocabulary that came up in today's task. So the first word we have of term is linear function. And so we say that equations that represent arithmetic sequences are called linear functions. Right, so obviously in Mod 1 we worked a lot with these arithmetic sequences, and we knew, for example, that an explicit equation for an arithmetic an arithmetic sequence might look something like, let's say, f of x equals 10 minus 2x. So we called that our explicit equation for that arithmetic sequence. Well, now we're going to call these equations our linear function. So it's kind of a new name for something we've already been working with for a little while. Now, on the other hand, equations that represent geometric sequences are called exponential functions. So again, if you think back to Mod 1, we talked about an explicit equation for a geometric sequence might look something like f of x equals, 4 times 3 to the x. That was our explicit equation. And again, the idea here now is we're giving it a new name and calling it our exponential function. Okay, so here's what some problems are going to look like when you get to the Ready, Set, Go. So my directions here say to predict the next two terms in the sequence. Then state whether the function represented by the sequence is linear, exponential, or neither, and justify your answer. So again, we have this idea of justifying that we had in Mod 1, and that's still going to be our 2A on the rubric. So I'm just going to make a note here that justify still goes with our 2A. So if I look at this first example, first I can see that I'm decreasing here. So it means I must be either using subtraction or division. So I'm going to say, let's see, 5, it looks like to get from one term to the next, I have 5 and 3.5, so it looks like I'm subtracting 1.5. If I do 3.5 minus 1.5 again, I get here. So I notice a constant pattern here of subtracting 1.5. So if I have 0.5 minus 1.5, I'm going to have a negative 1. And then if I subtract 1.5 again, I'm going to have negative 2.5. So that's the first part, is just predicting the next two terms in the sequence. Now I have to decide whether the function represented by that sequence is linear, exponential, or neither. So here's how we want to think through that. In this case, I know I had a common difference here. I was subtracting by negative 1.5 every time. So that common difference tells me that I had an arithmetic sequence. So that's how I'm going to start. I'm just going to say, since this sequence has a common difference, right? That number that I'm subtracting over and over again is the common difference. It has a common difference of negative 1.5. That means it is arithmetic. So now I've identified that the sequence is arithmetic, but I still haven't answered the question of whether it's linear, exponential, or neither. So now what I need to say is that arithmetic sequences are represented by linear functions. So my answer here would be linear. Let me move that up so you can actually see what I wrote. So the idea is we identified a common difference, so we knew the sequence is arithmetic, and then we say arithmetic sequences are represented by linear functions. And again, that came right from our definition up here. We're connecting arithmetic sequences to linear functions. So let's look at number 2. So the first thing I have to figure out is how to get to the next two terms in the sequence. So now my numbers are going up, so it could be that I'm using addition or multiplication. So let's say I think it's multiplication. So maybe I'm going to try doing times 2. Well, if I try to do that again, so 1 times 2 is 2, 2 times 2 still gives me 4, but then 4 times 2 doesn't give me 7. So I'm going to kind of put an X through here. What I thought might be a pattern doesn't hold up. Well, let's try to add. So to get from 1 to 2, I'm going to add 1. From 2 to 4, I'm adding 2. From 4 to 7, I'm adding 3. So something interesting is happening here. We don't have a common ratio because multiplying by 2 doesn't always work, and I don't have a common difference because I'm not adding by the same thing each time. However, I can see a pattern coming out here. I added 1 and then plus 2 plus 3, so my prediction would be then to get the next term, I would add 4. So 7 plus 4 would give me 11. And then I would assume that this would be a plus 5, and 11 plus 5 would give me 16. So I still am noticing a pattern and using that pattern to predict the next terms. However, this is going to be not linear because it's not an arithmetic sequence. It's not exponential because it's not geometric, so this would be neither. And so to justify, I would say the sequence does not have a common difference or common ratio. So it can't be arithmetic or geometric. So if it's not either one of those, it's not going to be represented by a linear or exponential. Because remember, those two ideas are tied to our arithmetic or geometric sequences. Okay, for the next part, our next set of vocabulary here is talking about continuous and discrete relationships and the difference between them. So here are the big ideas that we need to know. For a continuous relationship, we say that change happens gradually, which really means there's no sudden jumps. And if we were to look at a graph, the points on a graph are all connected. So here's what I want you to think of. An example here would be, let's say, filling a pool with a hose. Right? The idea here is if I'm filling a pool with a hose, the water is being added gradually over time. Now, when we talk about discrete relationships, we're talking about change happening suddenly. And we are going to see some jumps in whatever we're measuring. And so from a graphical perspective, that means the points on the graph are not connected. So here's what we can think about here. Thinking about filling our pool again, So we're filling a pool, but this time we're using a bucket. right? Now in this case, if I've got a bucket, water is going to be added very suddenly each time I dump a bucket in. So I'm going to say here the water is being added very suddenly. So each time I dump that bucket in, I get a sudden rush of water into the pool. So let's see if we can pick these ideas out when we're given certain scenarios. So here, our directions say to identify whether each of the following represents a discrete or continuous relationship. And again, here we're asked to explain our reasoning. And our explanations are going to use exactly what we talked about here. We want to think about whether change is happening gradually or whether things are happening very suddenly. So let's look here. So it says you decide to make fresh squeezed orange juice. You go to the store and you get a giant bag of oranges, but there's a hole in the bag. So on the walk home, you lose 2 oranges per minute. So our first decision is whether this is continuous or discrete. And again, we want to think about how that change is happening. So when I think about this, I'm thinking about the number of oranges in that bag. So if I'm walking home and I have a full bag, all of a sudden I'm going to notice that that number of oranges dropped. Since that change is going to happen suddenly, we would say this is a discrete relationship. And again, to explain it, we would say the number of oranges in the bag, number of oranges in the bag changes suddenly each time some fall out. For example, maybe I left the store with 10 oranges. When I check the next minute, all of a sudden, I'm only going to have 8 oranges in the bag. So it's going to be that sudden change that we're looking at. Now, for number 4, it says the average bamboo plant grows 3 to 5 feet every year. So if we think about how things grow, this is going to be more of a continuous relationship because that change, it's not like all of a sudden the bamboo plant is going to be 3 or 5 feet taller. That change is going to happen gradually. So we would say here, our explanation is that the height will change gradually, so little by little over time. Again, it's not suddenly going to grow 3 feet. That change is going to happen slowly or little by little over time, so we have a continuous relationship. All right, then the last one here, now we're looking at a graph. And the first thing I notice that is new compared to what we were doing in Module 1 is that all these points are connected here. That right away is going to tell me this is a continuous relationship. And the reason here we would say the points on the graph are connected. I don't know anything about the scenario, but I can tell by that graph everything's connected, so it's continuous. Okay, we've got one more thing to talk about. Our last part here now, we're going to focus on solving equations. And some of this may be familiar to you, but we kind of want to develop a consistent method for solving equations. So as these equations get more complex, we have a good structure for being able to solve them. Now, the first thing we want to mention, equation here, an equation always has an equal sign. So something like 4x plus 2 equals, let's say, 10. Right? Or negative x plus 1 equals negative 3. So the big idea here is that if it's going to be an equation, we have to see that equal sign. Okay. Now, inverse operations are going to be two operations that undo each other. So for example, when we talk about inverse operations, if I'm talking about addition, the operation that is going to undo addition, I would say the inverse is subtraction. The opposite is also true. So for subtraction, I know its inverse is addition, right? Then multiplication, and division are going to be inverses of each other as well. So for multiplication, the inverse is division. Sorry, I know I'm going out of the box here. And then finally for division, the inverse is multiplication. Now, the reason that this is important to us is because when solving equations, we're going to use those inverse operations to get the variable by itself. So in other words, we want to undo whatever was done to the variable so we can get it by itself. So let's take a look at a few examples. So for number 1, again, solving the following equations, we know if we're asked to solve here, our goal is to get the variable by itself. That's our big goal here, and we're going to use those inverse operations to do that. So for example, my goal is to get x by itself. Well, in my problem, 8 was subtracted from it, and I need to undo that. So again, in order to undo that subtraction, I'm going to use the inverse of addition. So here's how I like to set it up. I like to draw a line through the equal sign, so I keep organized between what needs to be on the left and what should be on the right. So if I want to undo subtraction, I'm going to use the inverse. So my negative changed to a plus, and I'm going to add that 8. The inverse of subtracting 8 is adding it. Now to keep my equation balanced, I need to do that on both sides. The nice thing that happens here is negative 8 plus 8 is just 0, so those are going to cancel and x is by itself. And now on the right side, if I do 10 plus 8, I get 18. So my solution is x equals 18. Now one nice thing about these equations is it's really easy to check and see if your answer is right. And here's how you can do that. Let's see, I'll use this color, hopefully it'll show up okay. I'm going to take my original equation was x minus 8 equals 10. I just found out I think that x is 18. So let's check. 18 minus 8, we're hoping that's equal to 10. In our case, if I do 18 minus 8, I do get 10, which is equal to 10, and we know we're right. So I recommend when you're solving, go ahead and check. It's a nice way to know right away if you're right or wrong. All right, let's look at number 2. Now in this case, I'm still going to go ahead and draw my line through there. Here I notice I'm dividing by 7. That's what this fraction means, is x divided by 7. If I want to undo division, I'm going to look over here. We said the inverse is multiplication. So I'm going to show multiplying, now this 2 is kind of in the way, I'm going to show by putting parentheses here that I'm multiplying by 7 on both sides. Now this 7 and the 7 in the denominator are going to cancel. I get x is equal to, and 2 times 7 is 14. Again, I can go ahead and check my answer. I think x was 14. So 14 divided by 7, again, I'm hoping is 2 if I was right. I can just plug into my calculator 14 over 7, and I'll get 2, which is equal to 2, and I know that I'm right. All right, last one. Okay, remember, I'm solving, so the goal is to get x by itself. Here I can see that 1/2 was added to my variable. I need to undo that so I can get my variable alone. Again, for addition, my inverse is subtracting. So instead of adding 1/2 here, I'm going to subtract 1/2 to both sides. Now I apologize, I don't have my calculator with me, but we would just type this in. Now 1/2 minus 1/2 is just going to be 0, so that cancels. I have x equals, now if you put 6.7 minus 1/2, let's see, we should get 6.2. So check that on your calculator. I'm doing that in my head. I could have certainly made a mistake, but that would be our value. So again, this is the structure we're going to use to solve equations, especially as they get more complex. It'll be a good way to organize our work. All right, I know this was a longer video because we had a lot of information to get through, but make sure you took good detailed notes and it'll help you a lot when you get to the Ready, Set, Go. All right, thanks for your attention.